Hello, welcome to the presentation of design and construction of an experimental apparatus for velocity determination of a gas bubble flowing in stagnant liquid. This work was done by André Ando, who designed, built, and conducted the experiments, by me, Luis Muzo, who was responsible for writing and presenting, and by Luis Lima, who was the professor who orientated this work. Starting with introduction and objectives, the subject of this work are the multiphase flows, which occur during the transport of mixtures containing gases, liquids, and solids. These flow types, they are present in many industries, for example, oil and gas, and nuclear energy. And one specific but very important case of multiphase flows are the two-phase gas-liquid flows. These flows they can be classified in many patterns related to the interface between phases, which are shown in this image. So this image shows the main gas-liquid flow patterns. The subject of this work is the slug flow, and the main feature of the slug flow is the presence of regions containing elongated gas bubbles, also called Taylor bubbles, followed by regions of liquid slugs, where liquid fills the whole section of the pipe, and these two regions repeat themselves along the flow. So in this context, it is important to improve the understanding and modeling of these flow types to ensure heat transfer and flow rates, for example, in those many industrial applications they have. The main goal of this work was to design and build an experimental apparatus to visualize and measure the velocity of an elongated gas bubble flowing in stagnant liquid, which is the two-phase gas-liquid slug flow. And also, experiments were carried out and compared against literature data in order to validate the apparatus. Many works were already conducted in the subject of an elongated bubble flowing in stagnant liquid from the 1950s to the present day, and they are better described in the literature review of the full article. Moving now to materials and methods. This image shows the experimental apparatus. It is composed of an aluminum profile structure, a 25.4 mm diameter 2 meter long pipe of transparent acrylic in order to visualize and measure the elongated bubble. These dimensions they show to be sufficient for the complete development of the Taylor bubble according to the literature review. It is also composed of an acrylic sheet with holes to allow inclinations of 0, 30, 45, 60, 75, and 90 degrees. And at the bottom of the apparatus, a section of 0.1 meter long pipe of PVC between ball valves for gas retention. So when the upper valve is open, the gas flows naturally upwards, forming the Taylor bubble flowing in the stagnant liquid. With the experimental apparatus built, experiments were carried out with air flowing in stagnant water. Two inclinations were analyzed, vertical, 90 degrees, and inclined pipe, inclined at 45 degrees, with 10 measurements for each of them, 10 measurements of velocity. The bubble ascension velocity was determined by video recording by a cell phone camera and posterior video processing by the shortcut application, and this velocity was calculated from the time intervals taken by the bubble tip to travel the linear distance of 0.5 meters between two marks on the pipe. I will show you these two marks in the video next. Also, the Freud number was calculated. This Freud number is the dimensionless parameter directly related to the velocity of the elongated bubble, and it is used for comparison against experimental data from literature review. And these calculated values were compared against experimental data from Gomes-Bueno from 2010 and against correlation by Bendixen from 1984. Moving now to results and discussion. This video shows one of the 10 measurements taken with the vertical pipe. So it is possible to see the formation of the Taylor bubble, followed by the liquid slug. And it's also possible to visualize the two white marks of the linear distance of 0.5 meters. This next video shows one of the measurements taken with an inclined pipe. So again, the formation of the Taylor bubble, followed by the liquid slug. And with all the measurements taken, now table 4 shows the average values of the velocity with its corresponding standard deviation and Froude number. So for the inclination of 90 degrees, the vertical case, the average velocity was 0.172 meters per second. And for the inclined pipe at 45 degrees, the average velocity was 0.245 meters per second. So the bubble moves faster inside the inclined pipe. With these values calculated, now table 5 shows the comparison of the Froude numbers obtained in this work against experimental values from Gomes-Bueno and against correlation by Bendixen. Against the experimental values from Gomes-Bueno, negligible deviations were obtained, up to 2.51% against the inclined pipe. This small deviation is justified by the different methods for bubble velocity determination. Now against correlation by Bendixen, again against the 90 degrees case, the vertical case, it showed negligible deviation. However, against the inclined pipe, it showed higher deviation of 21.72%. But this higher deviation was not unexpected, as other authors already concluded that correlation by Bendixen shows higher deviation against experimental data with inclined pipes. So, conclusions and future work. The apparatus was built and validated, and it is currently installed in the Didactic Fluid Dynamics Laboratory from the Ponta Grossa campus of the Federal University of Technology from Paraná. It is already being adapted to use impedance sensors to detect the passage of the Taylor bubble and automatically record its velocity, so video capture and processing would not be necessary. And future works could be conducted to investigate the effects of pipe geometry, diameter, and inclination, as well as the effects of other fluid properties such as viscosity. So we would like to thank Fundação Araucária for the scholarship awarded to André Ando, CAPES for the scholarship awarded to Luiz Muso, and the Federal University of Technology from Paraná for all the support during the development of this work and for the participation in this event. We also would like to thank you for watching this presentation till the end. Thank you very much.